All right, so this is section 7.1 on geometric sequences. Now, remember that sequences are really just our patterns of numbers, just like before we talked about arithmetic sequences. Now we're talking about geometric sequences. So consider the sequence 3, 6, 12, 24. What pattern do you notice? Just because I am, again, the same way I said in the zombie video, just because I'm a video on the screen instead of a teacher standing in the room with you, I am going to pause at times or stop talking and ask you to talk to your neighbors. So this is when I want you to talk to your table, your group. What do you notice about the pattern? All right, back to me. Hopefully you saw that in this pattern, every time it's just like our zombie pattern, it is multiplying by 2. Now, I feel like my first inclination might be to say that this is adding 3, which is true. It is adding 3 for that term, but then it's adding 6 and adding 12. So it doesn't have a common difference. It doesn't have the same amount that it's changing by every time. But it does have what we're about to learn. It's called a common ratio. It is multiplying by the same thing every time. So for that reason, it's a geometric sequence. Each term in the sequence is the blank of the previous term and some number r. So the previous term and some number are being multiplied, so it is the product of the previous term and some real number r. So just like our arithmetic sequences from before, we can represent this sequence in a table. So term 1 is a sub 1, which is 3, 6, 12, 24, 48. Now, for this one, our a sub n is actually going to be, the a sub n minus 1, which means the term before it. Now, what was happening to the term before it? From 3 to 6, and 6 to 12, and 12 to 24, and 24 to 48, what was happening? You're right, it was multiplying by 2. So it's the a sub n minus 1 times 2. Remember from arithmetic, this is called the recursive formula. And all the recursive formula means is if you know the number that comes before a number in the sequence, then you can multiply, and you know the common ratio, you can multiply those two things to find the next one. So then, how can we find, back to this table, sorry. So f of 1 is the formula to find the first term. F of 2 would be the formula to find the second term. F of 3 would be to find the third term. F of 4 would be to find the fourth term. F of 5 would be to find the fifth term. And f of n would be used to find the nth term. So then, how can we find the 10th term of this sequence? We can use the recursive process. That's one way. So the recursive process, again, like we said down here where we called this the recursive formula, the recursive process means we use the term before it. So we're going to use the term that came before and then use that common ratio. So a sub 1 was 3. We said 3 times 2 to get 6, and 6 times 2 to get 12. 12 times 2, 24. 24 times 2 is 48. 48 times 2 is 96. 96 times 2 is 192. 192 times 2 is 384. So then, for this one, we would say 384 times 2, which would give us 768. And then what do you think we would do for this last one? You're right. 768 times 2 would give us 1,536. So for every one of these, we just multiplied the term before it by 2 because in this one, 2 is my common ratio. 2 is not always my common ratio, but for this one, it is. So in function notation, that would be a sub 1, 2 times a sub 1, 2 times a sub 2, 2 times a sub 3. These are not exponents. These are just indicators of which part of which term we're talking about. So we're talking about the first term and the second term and the third term and fourth term and so on, all the way down here. So we could write a recursive formula that we could use to find any term in this sequence. So the recursive formula to find any term in this sequence would be a sub n is equal to a sub n minus 1, which means the term before. So if you want to write that down here, that might be helpful. The term before times, in this case, 2. This is my common ratio. Okay, so the term before it times the common ratio. So a sub n minus 1 times 2. All right, let's continue. Turn the page. Now we're talking about the explicit process. The explicit process, unlike the recursive process, the explicit process can help us jump to any number. We don't have to necessarily know the number before it to be able to find whatever term we're looking for. So for this same, we're looking at the same pattern here, starting with 3 and multiplying by 2 every time. So we said 3 times 2 is 6. But then this time, instead of saying 6 times 2, they said 3 times 2 times 2, which is the same thing as 3 times 2 to the second. So they still went back to that first term. And what you'll notice is on every single one of these, they go back to that first term, that 3. And then the number of 3's changes from there. So I'm going to point out something and then I want you to have a table talk. So just get ready for that. So this is 1, 2. So this is like 2 to the first, right? And this is 2 to the second. So term 2 has 2 to the first. Term 3 has 2 to the second. Term 4 has 2 to the third. Term 5 has 2 to the fourth. Term 6 has 2 to the fifth. Term 7 has 2 to the sixth. Term 8 has 2 to the seventh. Now, before you start talking, let me relay the question. So the question is, what do you think we could use to shortcut to get to terms 9 and 10? So talk to your table. I'm going to give you about 30 seconds. Okay, so I heard a little bit of the conversation. So I think that what you said is, well, if this was 2 and 1, that's like 1 less, and 3 and 2, that's like 1 less, and 4 and 3, that's like 1 less, and 5 and 4, that's 1 less, and 6 and 5, and 7 and 6, and 8 and 7, so I bet it's going to be 9 and 8. And since I'm still using that 3, it's going to be 3, and it's going to be 8 2's. So 1, 2, 3, 4, 5, 6, 7, 8, which is the same thing as 3 times 2 to the 8th power. So not 28, I had to write it tiny, but it's 2 to the 8th power. Okay? Which is the same as what it was before. 3 times 2 to the 8th power is 768. Okay, and then my next one is 3. If this is 10, we're going to go 1 less. So that's times 2 to the 9th. So 3 and then 9 2's. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 3 times 2 to the 9th power, which is the same as what it was before, 1,536. So as we go down this table, the function notation table, A of 1 was a sub 1. A of 2 was 2 times a sub 1. 2 squared times a sub 1. 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, 2 to the eighth times a sub 1, and 2 to the ninth times a sub 1. Oh, sorry, not a to the first, a sub 1. And the bottom. Okay, so the explicit formula for that would mean that we still take, so a sub n, it means we're looking for the nth term, for some number term. So to find a sub n, what did we use consistently in every single one of these? What number? Right, we consistently used 3. 3 was my first term, and we labeled that a sub 1. That's really important. A sub 1 was important for arithmetic, and a sub 1 is also really important for geometric. So a sub 1 was multiplied every time times a certain number of 2's. Now remember that 2, so this is my first term. Let's label that. And then 2 was my common ratio, that common thing that was being multiplied every time. So it was times 2. But this time, instead of only multiplying by 2 once, since I am trying to find any numbered term, I'm not multiplying by the term right before it. This is not a sub n minus 1. This is just a sub 1. This is the first term. I have to have an exponent on this. Now, remember my exponent was always my term minus 1. So when it was 10, it was 9. 9, 8, 7, 8, 7, 7, 6, 6, 5, 5, 4, 4, 3, 3, 2, 2, 1. Okay, so on every one of those, my exponent was 1 less than n. 1 less than n is just n minus 1. So this is super important. This might look a little familiar to you because our explicit formula for arithmetic sequences was very similar in that it had the n minus 1 in there. But we'll look at both of those together in section 8. So let's continue. Sketch the graph of the geometric sequence found in the table. So as we sketch this graph, we obviously are not going to be able to fit all of these on this graph without doing some form of abbreviation in our graph. So let's count by maybe 5s going up this way. So 5, 10. It's going to be a tight squeeze, but I think we made it. Okay, so you should go up to 105 on that side. And then going across the bottom, we have a lot of room to spread out. So we could even break this down to where maybe every 2 blocks is 1, or maybe even every 3 blocks is 1. So that's 1, 2, 3, 3, 4, 5, 6. That way you just have a little more space to breathe in the bottom since this is so cramped. So once we have it set up, the thing with graphing exponentials on graphs like this is we can't be perfect here. We're really just going to have to be okay with guesstimating where some of these numbers might be, like the number 1, 3. So 1, 3, I'm going to say it's about there. It's a little less than 5, but a little more than halfway. So there's 1, 3. 2, 6 is going to be a little bit more than 5, just a tiny bit more. 3, 12 is going to fall between 10 and 15. It's a little bit less than half between there. 4, 24. So 4, a little bit less than 25. 5, 48. and 696. So as you probably noticed, this got really steep really fast. If we were to graph this curve, well, it doesn't say that it's continuous, so I'm not actually going to connect it. But looking at this curve, this is an exponential set of data. It is curving upward, okay? It's increasing, but it's increasing exponentially because the way we know that it's increasing exponentially, you could recognize that from the shape of the graph, but also because it's multiplying times 2 every time. So it's a geometric sequence increasing exponentially. Down here at the bottom, the recursive process uses the previous term. That's important. Recursive uses the previous term, where the explicit process always goes back to the first term. Recursive is previous, and then explicit is the first term. Continuing on, let's practice. So consider this sequence, -2, 4, -8, and 16. Write a recursive formula for this sequence. So let's identify some things about it from the start. So recursive formula, if you flip to the very, very, very back of your workbook, so on the very back page or cover, it says geometric sequences. Well, let's hold off on that. Sorry, don't flip there yet. Come back and then we'll talk about that when we get to explicit, because the one listed in the back is actually the explicit formula. But the recursive formula for any sequence, you could write this at the top, for any geometric, is a sub n equals a sub n minus 1, the number before it, times that common ratio. The explicit is a sub n equals a sub 1, so that's that first term, times the common ratio. But remember, this common ratio needs an exponent. The same way the 2's on this one had an exponent, and that exponent was 1 less than this. Don't forget, okay, you had it here. You can still have this. This exponent was 1 less, so that's where my n minus 1 comes from. These two, when we're talking about geometric sequences, are really important to you. Now, this one, where I was going to take you just a second ago, is listed on the back cover of your Algebra Nation workbook. So on the very back cover on that formula sheet, you will see a sub 1, it'll say geometric sequence, a sub 1 times r to the n minus 1. That's the formula, the explicit formula for the geometric sequence. So let's talk recursive first, since that's what it's asking for. A sub n equals a sub n minus 1. Well, we don't know what term it's looking for, so we're still going to put a sub n minus 1 because we're not sure what the term before it would be, times that common ratio. Well, let's analyze right here to get that common ratio. To get from -2 to 4, I'm multiplying times -2. To get from 4 to -8, I'm multiplying times -2. To get from -8 to positive 16, I'm multiplying times -2. So, answer out loud, please. What is the common ratio? You are correct. It is -2. So, times -2. If you wanted to write this as a sub n equals -2 times a to the n minus 1, that is just as accurate. It's actually maybe a little more mathematically correct in the right order with that variable following that coefficient. So then an explicit formula for this one would be a sub n equals, you have your a sub 1, which is your first term. So in this sequence, my first term is -2. So -2, my a sub 1, times my common ratio, which was also -2, because that's what I'm multiplying by, raised to the n minus 1. Now, one thing that's tricky here, remember that if we raise a negative to an exponent, we always want to put parentheses around this, because when we type this in the calculator, if there's not parentheses around a negative number and you try to raise it to an exponent, it's not going to do it as you want it to. It's not going to include that negative as it raises it to the second or third or whatever power. Okay? Now, we want to find the 12th term of the sequence. So you have an option here. You could either come to the side and make a table and start with your -2, 4, -8, 12, keep going until you get to the 12th term. Or you could use this formula right here. If you're trying to find a certain term, the explicit formula is always the best one to use to jump forward to a certain term. Now, if it asked for the 5th term, I might use recursive because I know the 4th. So I would just say 16 times -2 and get the 5th term. But for the 12th term, that might take a little more work. So I'm going to say a sub 12. I'm going to use the explicit and say a sub 12 equals -2 times -2 to the 12 minus 1. So I have -2 times -2 to the 11th. -2 to the 11th is -2048. So -2 times -2048, which gives me a sub 12 is equal to 4096. Okay, so I want you to do the try it. I'm going to give you 3 minutes, so you can just let the video play as a class, and in 3 minutes, I'll start talking again. All right, so it's been about 3 minutes. So come back to me, please. So for recursive, remember we need the term in front of it. So we need to know what came in front of it. So that was a sub n equals a sub n minus 1, that's the term before, times that common ratio. So 7 to 14, 14 to 28, and 28 to 56 all are being multiplied by 2. So my common ratio, or my R, is 2. So you could have written it like this, or you could have written it like this. Okay, how many of you were able to get that? Great, good job. Rock stars. Keep rocking. Okay, so the explicit formula for this one is a sub n equals. Now for explicit, I always go back to the first term. So the first term here was 7 times my common ratio, which was 2, to the n minus 1. Now, One common thing that I've seen people try to do as we're doing geometric or arithmetic sequences even, you cannot multiply 7 times 2. Okay? This has an exponent on it. This 2 is being raised to the n minus 1. This 7 is not. So we can't say this is 14 to the n minus 1. Do not multiply the 7 times the 2. Understood? Okay, great. So then if it says find the 20th term of the sequence, what that means is that n equals 20. So in the place of n, in my explicit formula, I'm going to put 20. Now, this is a prime example of when I probably would not want to use the recursive formula. Technically, you still could, but we don't want to kill trees or waste our time. So it would just take a while because you're at the 4th term, so then you got to get to the 5th, 6th, 7th, all the way to the 20th. You're just going to have a long, long list of numbers. But if you're determined to do it that way, go for it. However, I would strongly recommend using the explicit formula for this one. So the explicit formula would be a sub 20 equals 7 times 2 to the 20 minus 1. So then we have a sub 20 equals 7 times 2 to the 19th power. 2 to the 19th power, grab a calculator, is 524,288 times 7, because it was times that first term. So then a sub 20 is equal to 3,670,016. Okay, so this is pretty cool. We can use it to find a lot of different things. If we went back to our zombie illustration from the beginning, it's similar to this in that it's doubling every time. So it's like there were 7 people infected, and then those 7 infected 7 more, and then those 14 infected 14 more, and so on, to where it's doubling every time. This one was doubling and the opposite. Sometimes if my common ratio was 3, it'd be tripling or things like that. So let's go on to the beat the test. So for this beat the test, it says an art gallery was showcasing a 6-inch long photo of a geometric landscape. The picture was enlarged 10 times, each time by 125% of the previous picture. Enter formulas that will give the length of each enlarged print. So it kind of breaks it down for you here. Of the a sub 1 is 6. Okay, let's also go ahead and identify, it doesn't ask you to do this, but I think it would be helpful. Let's go ahead and identify that R, that common ratio. So if each time it's being enlarged by 125%. So if it was being enlarged by 200%, what would it be multiplied by? It would be multiplied by 2, you're right. So if it was being multiplied by 150%, what would it be multiplied by? Okay, maybe not. What if it was multiplied by 50%? Right, 0.5, it'd be half. So if it was multiplied by 50%, it'd be 0.5. What if it was multiplied by 25%? It'd be 0.25, right? So we have 125%. Let's review percents here for a second. 125%. Well, that's the same thing as 1.25. Do you agree? The one whole is the 100%. The 0.25 is the 25%. Okay? So this is 1.25. My common ratio is 1.25 because of this 125%. We're going to multiply by 1.25 every time. So my recursive formula is just 1.25, that common ratio, times a to the n minus 1. If you wanted to write it as a to the n minus 1, times 1.25, that would be just fine as well. The explicit formula is very similar. It still uses the common ratio, but remember the explicit formula goes back to the first term. So from up here where we wrote it, a sub n equals a sub 1 times r to the n minus 1. So a sub 1 was 6 times my r was 1.25. I'm going to put it in parentheses just because it's a little more to write, to the n minus 1 power. Okay, so we can answer any questions now based on this explicit or this recursive formula. I just wanted to remind you guys, while I have your attention for a second, of a few important things. So first of all, there will be no tutoring today. Starting next week, there will be no tutoring this week, actually. Just to kind of get things coming back into the swing. Starting next week, there will be only tutoring on Tuesdays and Wednesdays. There will be a new schedule posted on Schoology for you to read and kind of see what's going on with Miss Rayburn and I. And then the other important announcement is that your homework is on Schoology. Okay? Everything will be posted there for you. If you feel that you need help, that you're not getting in here, that you're not getting from this video or from drop-ins from a teacher or from wherever, then please stop by to see Miss Rayburn or I first thing in the morning. You could come between 7:45 and 8:30, or you could stop by after school. We do not have tutoring this week, but if you need to stop by my room, Miss Rayburn might be at practice, but if you need to stop by my room right after school, I'm okay with that. Stop by, ask me a question, and then when we have tutoring next week, you're welcome to stay for that as well. Okay? You guys are not on an island. Please know you have lots of people here to help you. So let me know if you have any questions. Also, I'm going to post a link on your Schoology to a Flipgrid that is now open to all algebra students. So use that wisely. Use it to help you and each other learn. Okay, let's make sure we're not spamming it, not misusing it, or I'll have to take it down. But post questions there. Look for people's questions you can answer, and have a great day. Make sure you sign the card for Miss Davis. Okay? Have a great day.